Hi, everyone. My name is Eric Brandwein, and I'm a Vice President and Distinguished Engineer with the Amazon Security Team. When I joined Amazon, I was working on VPC, Virtual Private Cloud, the networking layer that runs underneath all our services. But a few years into my time at Amazon, we formed the new AWS Security Team. At the time, Andy Jassy understood something that I didn't yet understand. AWS is a trust-based business. We're asking our customers to trust us with their most sensitive data and with the workloads on that data. I figured I'd spend a year or two getting the security team going and then go back to my day job building services. Instead, I spent the past 15 years in security at Amazon. It's given me an incredibly privileged position from which to watch AWS grow and to get involved across everything. For the majority of those 15 years, I've been working with Colin McCarthy, who's also a Vice President and Distinguished Engineer, but he's in EC2 networking. In this talk, we'll tell you about some of the things that we do to earn your trust and to maintain it. Over the years, we've talked a lot about the shared responsibility model in various fora. In all honesty, whenever someone says shared responsibility model, in my head, a picture of a castle immediately appears. There's a ton of content out there how to build securely in AWS, how to uphold your side of the shared responsibility model. This is so important to us that we've got an entire conference dedicated to security in AWS. And by the way, thank you for joining us here in Philadelphia. However, that's not this talk. The strongest castle will collapse if it doesn't have a good foundation. The most robust castle, built on sand or perhaps in a swamp, will not stand. A castle built on solid rock will deliver the full strength of that castle. And so this part of the castle is yours to build. You get to make all sorts of decisions, determine how things are configured, how much risk you're willing to accept. If there's something you don't like in this part of the castle, you can fix it. This part of the castle is ours. If there's something you don't like down here, you can't fix it. You have to rely on us. We have to decide how to build it, and we're keenly aware that we're supporting the aggregate trust that you all have placed in us. We have to build services that delight all of our customers, from those just getting started through the most regulated and security conscious. That's this talk. We're going to give you some insight into how we build, how we think about building, and give you some actionable advice for selecting a cloud provider. Picking an infrastructure services provider is the start of a long-term relationship. This is a decision that you have to make with care. Your goal is to deliver for your customers. Your time is best spent growing your offerings and delighting your customers, not in a seemingly endless series of migrations from one provider to another. The best possible state here is one where you've found a long-term partner, a provider that you can trust now and can continue to trust for the future. Do your homework, ask hard questions, make sure that your trust is well placed. If you take one thing away from this talk, it should be the two questions that I'm going to introduce on this slide. I'm a tenured senior engineer, which is just a polite way of saying that I've personally made all the common mistakes and a few of the uncommon ones. I've learned that it's necessary to build your service well, but just doing that is far from sufficient. What really makes the difference is how you operate it for all the weeks and months and years that customers are going to be using it. All of our services make some set of promises to our customers. Sometimes failures in those promises are obvious. If you attempt to launch an EC2 instance and no instance gets launched, then it's clear to everyone that something went wrong. However, sometimes these promises are not as obvious. For things like our internal encryption controls, we could still respond to queries and launch instances and respond to customer APIs, even if we were failing to encrypt correctly. The service would still be working, but we'd be breaking a customer promise. That's not okay. If we're going to live up to the trust that our customers have placed in us, it's not sufficient to build a service that fulfills these promises. Sure, we'd know on launch day that we got it right, but we need to know every day, every hour, from the day of launch until the day the last customer moves off that service, that it's still right. Clearly, you're going to want to select a service provider that has world-class security services and features and partners. But again, that's not good enough. It doesn't matter how awesomely they think it works. It has to actually be that awesome today and tomorrow. That gives us our first question. You should ask, how does AWS know they're meeting all the customer promises they make? Ask your prospective providers, ask your current provider. Understand how they're thinking about all of the days after launch day. A good partner will have a web of interlocking mechanisms to help to prevent, detect, and respond to failures. I love working on security in AWS, and I love talking about it, but why should you believe me? The blunt reality is that I work for AWS, and our business does better when more people use our services. I am a biased participant in this conversation. You should require evidence, and that brings us to the second question. How can a customer know that AWS is meeting its customer promises? There are two primary ways that you can verify that AWS does what it says it does. The first is our open source contributions. Things like the Firecracker hypervisor and the S2N TLS library are fully open source. You can download them, read the code, read what others have written about them, and come to your own conclusions. The other is our deep investment in assurance and compliance. AWS supports 143 standards and compliance certificates worldwide. Our compliance reports and attestation documents are available self-service via our Artifact service. And so in this talk, we'll present some of the things that we do to maintain customer trust, and we'll answer these two questions for each of them. And to start with that, I'd like to bring Colm on stage.
Thank you, Eric. So I've worked at AWS for 17 years, and I want to take you back to 2009 to something called the pizza attack. You probably don't remember or haven't heard of the pizza attack, but it was a vulnerability found by Marsh Ray in November 2009. And he called it the pizza attack because in his demo for the vulnerability, he was able to order a pizza that he hadn't paid for, which is really cool. Now, at the time, we classified this attack as low risk and low impact for AWS and for Amazon. It required a lot of esoteric conditions to exploit that didn't really apply to our systems. In fact, we thought we don't have anything that's at risk or vulnerable to this attack. But nevertheless, you don't want to leave things lie. You want to have mitigation whenever you can, and you never know what else might show up in a new area of interest. So we decided we would have to update all of our systems to mitigate for this issue anyway. And what that looked like was we had a tight team of experts who were charged with doing everything from updating all of our code, all of our systems, and even going on premises with our vendors and making sure that they were mitigating this correctly, and then updating all of our systems. And we had actually had to do this during the week of Thanksgiving in November 2009, which is traditionally Amazon's busiest sales week, that week and the week after, and at the time was the busiest week at AWS. But we decided we still had to do this. Our CEO, Jeff Bezos, was personally briefed on this issue, kept in the loop throughout the whole process. And that was the first time I got a real view of just how deep our culture of security runs at AWS. And in all the years since, I've gotten more and more sense of that, and I break it down into a few different things and how I see us approach that security. Now, whenever you've got a function that requires expertise at a company, you've got two main choices for how that should be organized. If you've, say, got a finance team or a HR team, you can say, well, we want to embed that in every single team. We want to have an embedded finance person in every team so that the finance expertise is right there where we need it. Or you can have a dedicated, separate org, and you can put all the experts together. You can have a finance org, and all the finance people are in that org. But when it comes to security, the answer for what we like to do in this case is actually to do both. At AWS, we integrate security and security experts directly into our service teams, and we have an independent security org to keep us accountable and to act as a check and a balance. What that looks like is that people like me who are building services and shipping new features are expected to maintain our own expertise in security. We also have embedded security engineers, security champions, security guardians, who are doing nothing else except paying attention to security for our service, our features, our products. And then we also work closely with that independent AWS security org, everything from collaborating on whiteboards to doing our pen tests and so on. We do both. The next is that we expect our leaders to pay a lot of personal attention to security. Every week at AWS, we have a security meeting with our leadership team, including our CEO. They are putting the time aside to dive deep and drill into our security response and our security posture. If we ever have an urgent security issue or something that requires investigation, we are briefing these same people, and these are the people you'll see doing keynotes at Inforce or reInvent. We brief them within minutes, and I've never seen them not make the time. We're able to page them and engage them if we need them. It's pretty amazing. Next, security isn't optional. It's integrated into our development process and how we ship features. We cannot ship a new service or a new feature unless it meets our security bar, and we will not compromise on that. We will delay a feature or service if necessary, because ultimately we know that security is the feature customers care most about. Even if a service or a feature is something customers have been telling us they're eagerly awaiting it, they're really keen and excited to get it in their hands, we are too, we still won't compromise on this because it's a core cultural value for us. And then lastly, at our scale, we can't just preach about security. It's not just about proselytizing, and we can't simply ask people to try harder on security. Everybody's trying their best no matter what. We have to mechanize and automate security, and that means building it into our tools, libraries, frameworks, and templates, so that when a developer is building something new, it's secure out of the box, that the golden path is full of great defaults. And across all of this, my experience is that we have an enormous focus on defense in depth, unlike what I've experienced anywhere else. We want to ensure that we build secure systems, but we also anticipate that our security systems will fail, and one alone is not enough. We always want multiple layers of security, and ideally for one or more of those layers to be very general and capable of catching broad and wide classes of issues. Now this sounds just like good, responsible engineering. Reminds me a lot of resilient and highly available systems where you always want redundancy. If one system fails, another takes over and so on, and you continue good operations. But in security, my experience is it's actually a little bit different and stronger than that too, in that this defense in depth and layering also acts as cultural reinforcement for us. If we have a kink in one of our layers, or even just a suspected issue or a kink in one of our layers, we run our full root cause analysis process, do a full thorough investigation, and all of those details, super fine-grained details, will be presented at that weekly security meeting with the eyes of our leaders and even our CEO. We don't wait for an incident or an issue that actually exposes data where many layers have to have failed for that to trigger. We trigger it just on one or even a suspected issue in any one of those layers, which keeps us on our toes and lets us know how to stay paranoid. Now I want to cover an area where we have a lot of this defense in depth and how it's evolved over the years and why, just to serve as an example, which is how we do network encryption. So as you heard at the keynote, if you've ever learned about networking, you'll certainly have encountered the OSI layer model, where it has low-level layers like the physical layer, copper, or a fiber cable, all the way up to high-level layers like the application layer protocols, say HTTP for the web. And this is a really useful learning tool, but it's not really how real-world networks work. You know, starting even 20 years ago, it became common for networks and customers to use TLS and SSL and to encrypt traffic and to have this new encryption layer in the middle of networking. And TLS and SSL are great. They do provide end-to-end security. They do provide confidentiality. They do provide endpoint authentication, all of these really important security properties that we're familiar with. But there's some things that TLS and SSL don't do. TLS and SSL is not great at anonymity, for example. It doesn't hide whose traffic is whose or what volume of traffic is moving around. So as we built our virtual networking stack and added more kinds of encryption for customers, we've tried to add security properties in those layers so that the security we're getting and the defense in depth can be complementary to what we know customers are already doing. And I'll talk a little bit about that. None of this would be possible. We would not be able to encrypt all traffic at scale if we did not own our own highly optimized implementations of cryptography. And we have open source implementations of general purpose cryptography libraries, as well as implementations of TLS, Quick, a big number library. And importantly, we also have our own open source benchmarking suite, which means we're constantly measuring the performance and optimization of these implementations to make sure they're as tight as possible. And I want to give just one example, my favorite one of this work, which is modular inverse. So the modular inverse algorithm is just a mathematical algorithm that's really common to certain kinds of cryptography algorithms like ECDSA and ECDH. And before our optimization work, it would take 40 to 50 microseconds for one of these operations to occur. It's actually quite a long time. But we went in there and we decided we would optimize this for Graviton and other architectures and squeeze out every drop of performance that we could. And not just that, but to make the performance more consistent. And that consistency matters. For high reliability, you want nice, clean, predictable systems, but also for security, you want to make sure that there are no side channels being revealed through differences in timing and so on. So after our work, we were able to achieve an almost 10x increase in performance down to about 5 microseconds for this operation, which is a huge saving. And we're able to make it perfectly consistent because all of this is happening in constant time, which is pretty amazing. This kind of work, together with things like moving from the RSA signature algorithm to the ECDSA signature algorithm, mean we've been able to reduce our energy usage, fleet sizes, and help achieve our climate pledge goal. This stuff really can move the needle at scale. And so let's take a look at VPC encryption and how all of this feeds in there. So with VPC encryption, we natively encrypt in hardware all traffic between EC2 Nitro instances, whether that's between two instances that are owned by the same customer, or between different customers, or even if the traffic is going between regions when a customer is using cross-region peering. This is happening in real time at enormous performance rates. And as I mentioned earlier, TLS and SSL don't provide anonymity, but VPC encryption does. If you were to tap in and look at the actual traffic on the wire, you would not be able to see whose traffic is whose, which can protect customers from volumetric analysis, seeing who's having a busy day, seeing who's spinning up for activity and so on, which is an interesting threat model. And then below VPC encryption, we also have our lever network link encryption. And our lever network link encryption is encrypting every physical link between any two AWS data centers, including the entire AWS backbone. It's a huge system encrypting very large volumes of traffic. And this system too was architected from day one to provide complementary kinds of security. It also provides anonymity, and it also provides measures of post-quantum security. So let's look at that in more detail, and what post-quantum security is really about. So this is our Oscillate quantum chip, which is built on CAC qubits, quantum error correction, and advances in manufacturing that mean we have a real-world quantum chip. It can actually do quantum computations in the real world. Now, these systems are still early days and experimental, but as these systems scale, they're likely to get to the scale where they'll be capable of analyzing and breaking certain encryption algorithms. And so that raises a risk that today somebody could be capturing customer traffic, keeping it aside, and saying, someday we're going to try to crack that when a quantum computer exists. Now, how that actually works is that if you look inside a network encryption protocol, it's split up into several phases involving different algorithms. And at the high level, there's a handshake phase and there's a data encryption phase. In the handshake phase, everything's authenticated. You make sure you're talking to the right peer, and then you establish a key that's used by the bulk data encryption phase, which is where all the data is actually exchanged. Well, the good news is that the data encryption phase is largely quantum safe with today's encryption algorithms. Quantum computers do reduce by half the security strength of these algorithms, and half sounds like a lot, but it's not. There are many orders of magnitude of safety built into these algorithms. So merely having that security strength is not significant. It's still very safe in the face of a quantum computing threat. But within the handshake, the key agreement algorithms in particular are vulnerable to quantum computing analysis. So somebody could be capturing those key agreements and over time keeping a record of all the traffic, all of the keys, and trying to decrypt it later. So when we designed VPC encryption and our lever network encryption, we wanted to make sure that we were resilient to this long-term threat. And so in VPC encryption, we don't use a traditional key agreement protocol. We actually use pre-shared keys. And we have a control plane that's constantly distributing and rotating these pre-shared keys amongst all of the senders and receivers. We're actually at such a scale, our customers send so much traffic, and there are so many senders and receivers on VPC, that if we were to do this naively, it would actually exceed the safety limits and scale that AES itself was designed for, the bulk data encryption algorithm. So we're very intentional about sharding these keys and making sure we stay well away from those safety limits. But the benefit of using these pre-shared keys is that they're simply not vulnerable to that kind of analysis by a quantum computer natively. And on Lever, our physical network link encryption, we did something just a little different, which is we took a hybrid approach where we used a traditional key agreement algorithm and combined that with pre-shared keys so that we got the best of both worlds. So we didn't have to build a complicated control plane that spanned multiple AWS regions. That's not something we like to do for reliability and availability reasons. So we could still use a traditional key agreement protocol, but also mix in pre-shared keys so that we get that security against quantum computers. And as if that weren't enough, we go further and we do something called ratcheting, which is when a link is first brought up, we do that first handshake and that establishes a key, and then we start encrypting data with that key. Well, not too long later, we want to rotate that key. But when we do the next handshake, that's encrypted by the first key, and so on. The second handshake is encrypted by the first, and the third is encrypted by the second, and so on. And what that means is if an attacker really did want to be able to target any cryptographic vulnerabilities in these algorithms, they'd most likely have to keep all of the traffic that was ever sent on the link, from the very beginning, from when it was brought up, to whatever time they're interested in decrypting. So if it's 1 million keys later, they're going to have kept a copy of the 999,000 key and the 999,998th key and so on, all the way back to the first key. That's the only way they would be able to decrypt everything. And when you do the math, these links send so much traffic that there really just isn't enough storage out there that could actually store those kinds of volumes of traffic. So it's a very deep, robust kind of protection that you're getting. It's super interesting. And last thing we're doing, and the latest thing we're doing, is that we're now also deploying native post-quantum security to the TLS SSL layer. And we're doing that by replacing the legacy key agreement algorithms with new ones like ML-Chem that are designed to be resilient against quantum computing analysis from day one. And we're shipping this if you use the AWS KMS service, Secrets Manager, Certificates Manager, and other services today from clients such as the AWS SDK. This is happening natively. So you're now getting post-quantum security at 3 or more layers, all at the same time. How do you know we're doing all this? Well, this is my favorite answer to this from Eric's selection. All of this work is open source. We do this work natively in GitHub. We track it with GitHub issues. We have third parties who are constantly looking at this code as well, helping us do optimizations, helping us do security research as well. And it's all done in the open for everybody to see. If you're interested, I encourage you to take a look. And with that, I'm going to hand you back to Eric, who's going to talk about security and operations at AWS. Thank you.
Hello again, everyone. Humans and data don't mix. This is one of those glorious times where everyone's interests align. Obviously, from a security perspective, restricting access to systems and data is a good thing. Just as obviously, our customers want to limit our access to their data, ideally to zero. However, what makes this glorious is that reducing human access to systems and data is an availability win. Our services want their operators interacting with the hosts as infrequently as possible, ideally never. The problem with this is that it's hard. The reason that we have operators is to operate the services. There's a business reason. Every time they go to interact with those servers, there's a business reason for that access. And so in order to eliminate those accesses, you have to automate, to build tooling, and to eliminate the reasons for those interactions. So zero operator access is our gold standard. Not all of our services have gotten there, and not all of our services are going to get there. For example, our customers of AWS managed services expect our operators to be in there debugging, configuring, troubleshooting, helping customers run their AWS estates. And so that service is not going to get to zero operator access. So let's dig into a couple of the services on this list. Zero operator access doesn't mean that there was a day on which there was no operator access. It means that there's no way that an operator could get access. Not that we designed it that way, not that we launched it that way, but that it's still that way, despite the fact that we're constantly writing more software, launching new features, and bringing new people onto our teams. So KMS is our key management service. Customers can create and import keys, manage access to them. Most importantly, KMS is integrated across our services and is the foundation of the many encryption features that we offer. If you had to select one service to get to zero operator access, I expect you'd pick KMS. Bit for bit, encryption keys are the most sensitive data that we have, and KMS was built with zero operator access from the ground up. So the boxes there on the bottom are HSMs, hardware security modules. They are purpose-built hosts from the sheet metal in that we designed and built ourselves specifically to perform this role in KMS. And they've been certified by an external lab to FIPS 140-3 Level 3, which includes a verified lack of human access to key material. This means that the only way to interact with these hosts is through an API, and the only operations that you can perform are the operations that are offered by that API. And so KMS offers APIs like encrypt and decrypt and create key, but most importantly, there's no get key. There's no way to get a key out of KMS. Building a scalable, durable, performant, and compliant key management service is a big job, and we've been at this for well over a decade. KMS makes one primary promise to our customers. No human, whether they work for AWS or not, can ever get a key out of KMS. The design of KMS, with keys existing in clear text only on these dedicated purpose-built hardware boxes that were designed to have zero operator access from the start, is core to delivering on that customer promise. So one of the most critical things in KMS is that we trust only these HSMs that have been correctly added to the domain, running the correct, trusted software with the right secure configuration. We have a formal machine verifiable proof that the protocol for using what we manage the domain, what we call the domain membership, is correct. This proof shows that the secrecy of the domain keys, which are then used to encrypt customer keys, cannot be violated even against an internal adversary with operator credentials. And as Cole mentioned, AWS LC is our own cryptographic library. It's such a core function for us that we knew we needed to own this. We can't fulfill our KMS promise if our cryptographic building blocks aren't correct. And so AWS LC itself was built with care, with a strong focus on correctness, including a deep investment in formal proofs. We have machine verifiable proofs of the correctness of the cryptographic primitives and many other properties of this library. And these proofs run at build time. If any of the proofs fail on any build, the build fails and the software doesn't get pushed to production until someone comes in and fixes the underlying problem with the software and allows the proof to succeed. And given the proofs above, KMS should always work correctly. But it's not just built right. With every software change, we verify that it's still right. Even so, we still validate the behavior of the running system. And we have auditors that check the membership of the production domain, and it makes sure that each host has the same view of the production domain. It gets the configuration off of each host and makes sure it matches what should be in the production domain, and we're constantly verifying this. We've published a paper that we've done on the work for this domain management proof. So this is publicly available. You're welcome to check it out. Likewise, AWS LC is open source, and we've published much of the formal verification work that we've done on it. And of course, we have compliance controls to speak to this, both FIPS and SOC 2 controls. And so this is evidence that AWS is delivering on this customer promise. This is a diagram of the EC2 Nitro architecture. EC2 is a system that we had to bring up to the zero operator access bar. EC2 is old enough that when we built it, zero operator access wasn't even a term that people were using. And it's also one of our most foundational services. If you run a database in AWS or a Lambda function or use any of our AI and machine learning services, they're running on EC2 instances. It's absolutely crucial that we get the security right here. So the Nitro card, the blue box on the bottom, is where we run our software. This is a separate physical card with a processor that we made ourselves, and this provides a deep, clear separation between AWS and customer workloads. And this isn't an HSM. We don't have the FIPS requirements to eliminate human access, but we still took the choice to build Nitro from the beginning with zero operator access in production. And with Nitro, we had this fundamental change rolling out through the fleet, and it was an expensive change. However, everyone wanted it. Nitro gave us better performance, it gave us better availability, it gave us better fleet operations, and it also gave us better security. It wasn't cheap, but it was totally worth it. So as an engineer, whenever you can couple security value to something that the team already wants to deliver, drive hard. And so earlier I said, without human access in production, that's an important caveat. We have a package called the NDK, the Network Development Kit, and it enables remote access, and our builders install it when they're troubleshooting or debugging. And so without it, our development of Nitro would slow to a crawl. Our developers would have to do all of this debugging and troubleshooting through APIs that are intentionally designed to constrain their access. And so we expect the NDK to be installed on non-production hosts when our developers are engaged there. How do we ensure that the NDK is never installed on a production host that has customer data? So, as with all software shops, we have source code repository where all of our code is committed. And on commit, we automatically kick off builds, but these are development builds. Commit leads to development builds. On Nitro, we do 100% code signing. Every single one of the packages installed on a Nitro host is cryptographically signed, so we need a signing key. So we get the development key, sign the build, and the result of this is a package signed by the development key in the development package repository. And eventually, this package will get installed on a non-production host. Now, when the team determines that the software is ready for release to the fleet, we kick off a production build. This is entirely analogous to the development build, but we use the production signing key. And in this fleet, production is a formally defined state, and only hosts in a production state host or could host customer workloads. So we do a full secure boot on Nitro, and thus we have cryptographic assurance that only correctly signed packages are installed and running. Only unsigned code cannot be installed. Our production hosts only trust the production key. So if someone attempts to install a package signed by the development key, it fails and we cut a pager ticket. Our automation watches the build system. If someone submits the NDK as a production build, the build fails and we cut a pager ticket. If somehow the NDK were built using the production key, we watch the package repositories. If a copy of the NDK is signed by the production key, we remove it and we cut a pager ticket. We have an auditor that constantly walks the fleet. It verifies that every host in a production state only trusts the production signing key. It also verifies that all of the code installed on that host is signed by the production key. And again, if we have any exceptions, we cut a pager ticket. And every time we say this, we cut a pager ticket. That's a SEV2 ticket, a pager ticket. We literally page someone synchronously and with a 15-minute response, and we also engage the security team. And these mechanisms that I've described are owned by different teams in EC2, and so suppressing or bypassing these controls would require changes across multiple teams spread across our organization, and we've structured them that way intentionally. So we've not just built a system where human access isn't possible on launch day. We've built a network of controls that ensure that human access continues to be impossible for the life of this service. So how do we know? We have all of the things that we just went through, where at every stage, we're checking to make sure that the system is working the way that we expect it to work. How do you know? We had a respected external security firm do a deep dive in the Nitro system, and I encourage you to download the report and review what they found. So 0 is the best number, but if you're not there, there's still great value in driving down the rate at which your operators access hosts. You can drive to 0, and that makes things simple, but there's another magical point, and that's when you drive the rate of accesses down to the point where you can review every single one. That's when you can drive the operability, the security, and the availability of your service up. So we all have operators. They're at their laptops, and at least occasionally, they have to access some production host. As I'm sure you all do, we collect the logs from these hosts, and they get sent to a storage system. We use S3, of course, and then on to some analytical system where we analyze them for abnormalities, things that we don't want to see. One challenge here is that for the typical Linux system, these are the auth logs. You've got things like SSH accesses, who used sudo, things like that, but there's just not that much data in them. You can spot some problems in them, but based on these logs, you can't know that your systems are operating in an acceptable fashion. And so to address this, we have an operator monitoring system that uses eBPF and audit D-hooks in the kernel to monitor and log all of the activity on these servers, on all of the servers in the company. And so importantly, we get a record of every single process invocation from every host, and we can tie this back to an individual hardware MFA authenticated human. So now we know who's logging in and everything they did. This is a gold mine. Now we can do the analysis and understand what the most frequent reasons are for host access. Our analytical systems are way more valuable with this additional data. And if you have a mature system that's been running at scale for years with no back pressure, you're going to have hundreds of thousands or millions of accesses per month. And a lot of this is going to be scrappy tooling built by your developers. If you need to get disk I/O metrics across the entire fleet, it's way easier to just write a quick script, log into each box, run the command, parse the output. It's quick and easy from an efficiency perspective. But that developer connected to that host with a full shell, and the only thing they did was look for disk metrics, but they could have run any command. Even if they only needed to do one thing, they had access to do everything. So now that we have this data, we can use it to determine the most common reasons that operators are accessing hosts. There are things like restart a process, look at the logs. We could turn those into tools, automating and constraining their activity, but how do you do that? Turning everything into an API would be great, but that sounds like we've got the API team, this team that builds it. Now we've got the whole company blocked on one team. That's a bad idea. And these teams already have all of these operational tools, shell scripts and whatever else that they've built over the years. Can we reuse that? And so we not only need to build it, but we need to get it rolled out, not just across all of the servers, but across all of the operators as well. The humans have to use the tool. And so we built a constrained operations system. It's got a client component that runs on our client devices, It's both command line and web-based, whatever the developer is used to in that situation. And our operators invoke it there, and then it calls out to a server component, and it invokes verbs. So each of these operations gets wrapped up in a verb. And using the operator monitoring telemetry, we can often suggest the verbs that the teams need to build to drive their rate of accesses down the most. And so now that we've got this library full of verbs, things like start a process, look at the logs, get the metrics, we rank them by how safe they are, both operationally and from a security perspective. And so something like getting statistics is very safe. We're going to allow people to do that with no approvals. Restarting a process, that's a little bit more dangerous. Maybe there's some approvals there. Running arbitrary Unix commands, that's going to require a significantly higher set of approvals. And so now when we give someone access to run one of these verbs, that's way easier to grant from a security perspective. We've told them, here, you can go do this thing, rather than you can do anything, please only do this thing. And so once we rank these verbs, we categorize them. And again, we've got the things where we allow people to do them freely with no approvals, all the way up through a much more arduous set of approvals. And so how do we do that, though? I've been skipping a step in how our operators get access to hosts in Amazon. Authorization is the process of determining if a principal should be allowed to perform an action. And when granting access to our servers, we have to authorize these callers. So in reality, if I want to access a host, I actually call out to an authentication system, and I say, hey, I would like to log into this host. And the authorization system's like, oh, well, like this is allowed. Here's a key that will allow you to do that. And then I can use that key to start that session. Internally, this is all done using SSH certificates and a bunch of software that we've written. In the default mode of this system, this is a static list of users. Over time, these lists tend to get quite long. You know, there's a large set of employees that may need to have a business need to access the servers, but they don't have a need on that day. And every single one of those people that's on that list is a risk that you carry every day, even if they don't need that access. This is the design point for most systems because it's what's easy to do. If you've got a directory, Active Directory, LDAP, something like this, making groups of users is the easy thing to do. But because we have our own authorization system in the middle of this transaction, we can do a better job of reducing access while still enabling our operators. We call being smarter about this contingent authorization. Your access to a host or service, your authorization, is contingent on exactly what you're trying to do and why you're trying to do it. So now when I query the authorization service, I have to tell it what I'm trying to do, run this verb, and why I'm trying to do it. And in this case, it's a trouble ticket. And maybe it's a change management ID. Our change managements go through an approvals process. Maybe it's a customer service case. And in many cases, for example, with customer service cases, our employees don't even notice the pivot here. It's all automated completely. I'm working on behalf of this customer. I would like to get this metadata, and it just seamlessly happens. And so if I'm allowed, now I get a response back from the authorization service telling me, yep, Eric is allowed to do this thing. And even if we didn't take any extra authorization steps here, now we know what I'm trying to do and why I'm trying to do it, and that is an incredibly rich analytical data stream. So now I can use this signed key to authenticate to the server, but only to perform this one operation. Internally, we've done this by adding forced commands to SSH certificates and a bunch more software that we've written. We can check to make sure that I'm currently on call, that my connection is coming from an expected location, etc. If we can't programmatically verify that my access is appropriate, we can require a peer or a manager to approve my access. And this gets us, again, another robust log stream that's an absolute goldmine. We process these reports for our managers all the way up through Matt Garman. We also run a series of anomaly detectors across these logs looking for unusual activity. The justifications provided by employees, combined with the detailed transcripts of the commands they actually ran, is a rich field for the application of generative AI. And so using this feedback loop of recording in detail what happened, automating common operations, and pushing back on unnecessary accesses, repeated week after week, month after month, drives cultural change and greatly lowers the noise floor. Operators get better tools, common issues are automated away, and access becomes less frequent. And so that allows us to put more scrutiny on the remaining access and to require tighter justifications on the remaining ones, leading to a virtuous cycle. Our services are on this journey, and some of them, like Fargate and Lambda, have reached the end. We've eliminated all interactive human access to these hosts, including the ability to run arbitrary Unix commands via our constrained operator tools. So how do we know? As I mentioned, we have all of this telemetry, coverage, visibility, and the closed loop analysis all the way up through our CEO. We also have a number of compliance controls. We have SOC 2 controls. BSI is a German standard, and FINMA is a Swiss standard. Again, all of these are all available for self-service download on the Artifact service. And now, I'd like to bring Colm back.
Thank you, Eric. So I work with customers who are migrating often from on-premises and other legacy environments directly into the AWS cloud. And it still never ceases to amaze me how the biggest improvement they get the most quickly is moving and using the AWS Identity and Access Management service. Often these customers are moving from an environment where they have shared team accounts and no one really knows who did what. It's not so traceable. And they often even have a literal password book with the passwords written down in a desk drawer somewhere. Well, the Identity and Access Management service automates all that away, makes it easier than ever to have super fine-grained permissions and traceability. It's one of the core pillars of security on AWS. But all of that would be for nothing if IAM were simply doing the wrong thing. If we were letting the wrong people access the wrong resources or perform the wrong actions, it would be meaningless. It would also be meaningless if IAM were too hard to use. If customers were constantly creating misconfigurations that created either overly broad or too permissive or too restrictive an access policy. Both would kill an organization. And so we place a tremendous amount of focus on making sure that IAM is correct in its implementation and so that it's easy for customers to use it correctly. And the first pillar of how we do this is our approach with openness and transparency. We use IAM ourselves internally, pervasively. When one service calls another service on a customer's behalf, we're using the same IAM calls and APIs that customers can use. And we use per customer service linked roles. We log those events, customers can see them. Customers can even break them and deny those actions if they want to. And we publish the policies and permissions that we grant to those roles. They're in the AWS documentation, and we know that third parties and some AWS heroes pay pretty keen attention to those policies and constantly vet that we're not making them overly broad or also too restrictive. But we also constantly want to make sure that the implementation of IAM, the actual code and business logic that's checking only this person should have access to that and so on, is actually correct. That's one of the most critical layers to get right. And to do that, we use automated reasoning and formal methods. The first implementation of IAM when we first built the service was called Aspen. Over time, as we grew in scale, we realized we wanted to build a much more lightweight and performant and highly optimized implementation. We call that Balsa. And when we built Balsa, we decided from day one we would use automated reasoning and formal validation to ensure that it was correct and really getting the right answers. We also applied this same approach to Cedar, our open source policy language, which you can use in your own applications. And you can see how we do these techniques. And by using automated reasoning, we're relying on advanced simulation techniques where we're able to generalize and summarize huge combinations of all possible inputs and distill them down to a few cases that then have to be modeled mathematically through the system, and then check that simple invariants hold. Simple invariants like, well, only the right people should actually have access to the right things and so on. Let's make sure that the code truly respects that. But one of my favorite things about working at AWS is when we approach this, we didn't just say, well, we're just going to prove this mathematically and we're going to run the formal proofs, and at the end of it, we get a binary result, true or false, it's proved or not. That is hugely valuable. The main reason we're doing this is to prove that these systems are correct, but we wanted to get even more value out of this. We wanted these same techniques to be able to tell customers what these generalizations and summaries are, so that we could help people understand complex sets of policies and rules. And this is what powers IAM Access Analyzer. Access Analyzer is actually using the same automated reasoning and formal methods under the hood. It's doing these generalizations, and it's providing those generalizations as insights to you. So you can give it large, complicated policies and rule sets, and it will tell you in simple summaries, here's who has access to what and why. And we've integrated this deeply into our own processes. When we create managed policies and those other rule sets that we publish and show you what our permission sets are, the first thing we're doing whenever we create a new one of those rule sets or make a change is actually run it through Access Analyzer. Before we even do human review, before we even waste a security engineer's time, we're having Access Analyzer tell us and catch anything that would be overly broad or overly restrictive. And it's really tightly integrated and very, very powerful in my experience. How do you know we're doing this? You can look up our FedRAMP documentation. The references are on this slide. Now, at this point, when I'm explaining IAM and our correctness and the fact that we've formally validated the actual implementations, if there's a security engineer in the room, they often ask me, okay, but what if the IAM service itself were compromised? What if there was, you've proven all this business logic, but what happens if it fell into the hands of a malicious actor who simply overrides that logic? Well, it's not so simple. There are a lot of layers of defense in front of the IAM service. As you can imagine, it's one of our most heavily defended services. There are many layers of encryption, many layers of operator access control, many other layers of attestation and validation and so on too. But still, this kind of movie plot threat is a question worth asking. And it's a really interesting example of how our approach to checks and balances and independence and separation of concerns comes out. Because the way we think about it is, even in this kind of crazy movie plot worst case scenario where a core authorization system were compromised, we still want to ensure that all of our detective controls, all of our monitoring, everything else would still catch that, would still know instantly. And so if you look at CloudTrail, for example, our detective control, our logging system that shows customers the access attempts and accesses on their resources, you'd see that it's maintained by a separate team in a separate org. That's intentional. It is a separate, dedicated process on every machine. That's also intentional. By the way, that's a little inefficient and unoptimized. It would be better performance if we just had one tight piece of code that authorized and did access control and then immediately logged the event. That's not how it works. We intentionally have separate processes that are kept independent, different code paths, different everything as much as possible. And so that even in this event, we have an independent stream of what's going on that would make these kinds of misconfigurations apparent. The customers would still see that things are happening. And this is a really good example, I think, of how that separation of concerns and compensating controls works out in the real world. And it's not just about technical isolation, but about organizational isolation as well. Now, throughout this talk, we've covered a lot about our culture of security here at AWS. And we've given you references that you can look up to verify the statements that we've made on stage. But I hope we've also given you a first-person sense of just how deeply we do care about security at AWS and how it really is our number one priority for us and not a cultural value that we would compromise on. But that said, we are just always humbled by our customers. We know that we're building that infrastructural, foundational plumbing layer. It is our customers who are ultimately building the houses, hotels, offices, and castles that are built on top of that foundation and actually deliver those world-changing experiences to your end users, to your customers, and to citizens. And so we're just always eager and looking forward to seeing what you build on top of AWS and apply security patterns in how you do that too, so that all of those end users are as protected as possible. With that, thank you very much for coming to our talk on behalf of myself and Eric, and enjoy the rest of Inforce.